Efacec is the largest Portuguese company in the electromechanical industry sector. The Efacec Energia business unit provides a broad range of products and systems for the global energy market. Efacec Energia, in partnership with Altice Labs and IT Aveiro, is committed with one pilot for the energy vertical, one of the 4 vertical pilots of the 5Growth project. The Energy Vertical pilot aims to explore the capability and enhancements of the 5G technology provided by the 5Growth platform in integration with the 5G VINI infrastructure and services to enable smart management solutions for the energy market in the low-voltage distribution segment. The Energy Vertical pilot is based in 2 use cases deployed inside the perimeter of the University of Aveiro, and their main purpose is to demonstrate the capability to provide advanced monitoring and maintenance support, assisting the control center operator and the teams dispatched to the field to better assess the impact severity of the outage they are facing. For the energy pilot, a fully functional 5G standalone network is available, encompassing a 5G core and a 5G radio access network with the following components: central unit, distributed unit and radio unit. The 5G core and the CU plus DU were installed in the IT data center in IT Building 1. The 2 RUs were deployed in the secondary substation of the Aveiro University and in IT Building 2. The radio access network component is based on ASOC's Cyrus 2.0. ASOC provides a fully virtualized RAN solution, delivering standalone 5G cellular connectivity. It is fully virtualized across all layers and follows the Open RAN architecture, an open standard that decomposes the 3GPP G-Node B into 3 different components: the radio unit, the distributed unit, and the centralized unit. The decoupling of these components is one of the differentiating features of the Aveiro pilots. The CU and the DU can be deployed in different locations or can be co-located. The RU is in charge of converting radio signals into a digital stream for transmission over packet networks. Concerning the user equipment, multiple devices can be used, such as the Huawei 5G CPE Pro 2 used in the energy pilot. The different components of the radio access network can be managed and monitored to guarantee optimal performance. The 5G core is based on Fraunhofer Focus's Open 5G core. Open 5G core components, including all the fundamental 3GPP 5G core network functions, can be deployed as containers or virtual machines. Open 5G core follows the service-based architecture, in which self-contained, independent and reusable network functions expose their functionality through a well-defined REST interface. The O5GC command line interface enables configuration and monitoring of all the 5G core components. The integration of 5Growth with 5G VINI involves the adaptation of the 5G RVS requests to the Sonata Slice Manager. The flow between 5G RVS and the 5G VINI's network function virtualization orchestrator follows the 3GPP standard TS28531. 5Growth is used at the vertical side to map the use case service to an end-to-end slice request to the 5G VINI platform, to provision the 5G service including all the 5G core functions and related connections and configurations to the ASOC's 5G RAN. This integration has allowed in the availability of the interdomain and security innovations led by IT Aveiro and also supported in Sonata through extensions implemented on it. The 5G VINI monitoring platform was integrated with the 5Growth monitoring platform using the semantic data aggregator. The probes are placed in the pilot UEs and servers and periodically send data metrics such as latency, jitter, packet loss and average throughput to the 5G VINI monitoring platform. The 5Growth monitoring displays the collected metrics in visual form with Grafana subcomponent. The energy pilot unfolds in 2 different use cases: the advanced monitoring and maintenance support for the secondary MV/LV distribution substation, and the advanced critical signal and data exchange across wide smart metering and measurement infrastructures. Several probes are installed across the pilot components to measure latency, jitter and packet loss in the link, and to measure the average throughput in each interface. In the first use case, the operator in the control center gets real-time information concerning a fault occurring inside the secondary substation, including live telemetry of the electrical equipment and video streaming from the substation interior. This way supporting a faster and more accurate maintenance planning with a better evaluation of the human and physical needs to resolve the fault and restore the power supply, therefore reducing the utility OPEX. The 5G connectivity on the substation side is achieved through a Huawei 5G CPE Pro 2 connected to the Altice Labs 5G standalone network. One ASOC's RU deployed inside the secondary substation is connected by fiber optics to the ASOC CU plus DU and to the open 5G core solution. The control center system is deployed in the IT Aveiro data center, connected to the 5G core through the data center network. In the first use case demonstration, we'll see what happens when an abnormal event takes place inside the secondary distribution substation. For that purpose, we simulate a blown fuse event in one of the low voltage outfeeds, interrupting the current sensor reading. As the current reading is interrupted, a new alarm event shows up in the alarm list interface on the operator's screen. Other user interfaces like floating lists or diagrams are also immediately updated with the new status. To ensure a reliable real-time operation of the network and a smooth experience for the operator, a sustained low latency on the communications network is mandatory, not exceeding 100 milliseconds. The operator will then track down the abnormal event just arrived, opening the single-line diagram of the problematic substation from the alarm list entry. The diagram exhibits a set of real-time live information concerning the secondary substation telemetry, measurements like current and voltage, and signals like a blown fuse or an actuated intrusion detector. The operator may open a video streaming transmitting from inside the substation to get further information about the root cause of the abnormal event. This can be particularly useful to the operator assessing what is going on inside the substation. Maybe a fire on the power transformer or a human or animal intrusion. He can then pass accurate information to the maintenance team on the field, saving valuable time preparing the intervention to resolve the occurrence. Meanwhile, an incident ticket will be issued and assigned to a nearby field crew to investigate the fault event. The field crew has immediate access to the work order related to the incident using a 5G mobile device connected to the 5G network. With the mobile interface, the field crew can get real-time information from the secondary substation, such as the telemetry, the alarms, and the live video feed from inside the substation. This information helps the field crew to assess the fault in advance and better prepare to solve it. The team can use the geolocation of the secondary substation to establish the better route to get there. When the team enters the substation, the intrusion detector is actuated. The detector signal is acquired by the substation controller and immediately transmitted to the control center, showing in the operator workstation. That blinking door is telling the operator that something requires his immediate attention. Through the video streaming, the operator can follow the field crew actions while they investigate the root cause of the incident. This enhanced supervision of the secondary substation would not be possible with the communication technology currently deployed in the distribution network across the secondary substations. We are talking most commonly about GPRS, with very low throughput capabilities and higher latency than required for real-time remote operation. In the second use case, the low-voltage sensors installed in the IT building distribution cabinet and in the laboratory electrical switchboard transmit real-time telemetry and last-gasp events to the concentrator inside the substation, which forwards them to the control center. The low-voltage sensors are connected to the substation through the 5G standalone network. These sensors and the concentrator are time-synchronized by the IT NTP server. The low latency and the high availability of the 5G network are key points to keep the low-voltage sensors timely synchronized and to ensure that the last gasp events triggered by the low voltage sensors are transmitted as soon as they are generated and while these sensors have remaining power. In the second use case demonstration, we'll see how a power down incident in the low voltage distribution network is handled and transmitted to the control center. For that purpose, a power cut is simulated, affecting the electrical switchboard and interrupting the power supply of the low voltage sensor installed there. The voltage drop triggers the last gasp signal in the low voltage sensor. This signal is pushed into the 5G network to be acquired by the substation concentrator and immediately transmitted to the control center over the 5G radio connection. We can see that as soon as the power supply is interrupted, a new alarm event shows up in the alarm list interface on the operator screen. Other user interfaces, like floating lists or diagrams, are also immediately updated with the new alarm status and the related telemetry measurements. The operator opens the diagram of the distribution cabinet close to the electrical switchboard and realizes that this one is still energized. The fault must be in the circuit between the distribution cabinet and the electrical board. A few moments after the fault occurs, the control center operator already has valuable and accurate information to pass to the field crew that will be sent to investigate and solve the problem that led to the fault. The communication technologies currently in place in many of the metering infrastructures, like PLC Prime or RF Mesh, have limitations that prevent them from supporting a large-scale real-time monitoring of the low-voltage network. The 5G provides the performance and capacity to do the job. Several validation campaigns took place along the project, giving valuable indications to adjust the 5G network parameters to better cope with the use case's requirements. The graphics and tables here presented show the performance of the 5G standalone network in the final validation campaign. The most relevant core KPI on data rate of this pilot was measured in use case 1. The performances of the field trials of the 5G network at the vertical site to transmit the data flow in terms of UDP traffic between the secondary substation and the control center provided a good video streaming experience. During the test period, the service availability was 100% and no packet loss was detected up to 10 megabits per second. The data rate uplink could reach 60 megabits per second. The most relevant core KPI on latency was measured in use case 2. The last gasp information, end-to-end latency between the low-voltage sensors LVS3 installed in the low-voltage network and the G-Smart installed in the secondary substation was measured directly in the application, which was 27.94 milliseconds on average. The latency in the time synchronization service between the LVS3 device and the NTP server was 13.4 milliseconds average, achieving an average difference of 1.21 milliseconds between LVS3 devices when comparing each one's synchronized time. The business, functional and technical needs concerning the advanced monitoring and maintenance support for the secondary distribution substation and the low-voltage distribution network have been presented, along with the details concerning the implementation and deployment within the energy vertical pilot. A 5G standalone infrastructure was integrated, deployed and configured in the 5Growth pilot site at University of Aveiro, providing low latency and high data rate, supporting both real-time telemetry flow and video IP streaming requirements. The Energy Pilot's infrastructure allowed the integration and validation of 5Growth innovations and their interaction with 5G Vini, supported by the 5Growth stack. Taking the good results obtained, Efacec is considering the development of a business case, including the 5G connectivity service as part of the next-generation smart management solutions for the low-voltage electrical power distribution.